I'm Kirill Tchernyshyov. This is a talk about the origin and nature of oxygen-6 in gaseous atmospheres that I am calling, for the purposes of this video, What's the Deal with O6? This investigation is part of CGM Squared, a new spectroscopic survey of galaxies in QSO fields that features over 1,000 new redshifts of galaxies down to 24th magnitude in the G-band. It is complete to 22nd magnitude within 2 arc minutes of each QSO. Check out Wild et al. 2021 for more details. This study is galaxy-centric. We want to know how host galaxy properties affect O6 properties. To enable this study, we combine data from the literature with our new CGM squared measurements. This gives us a large sample covering a broad range of stellar masses and impact parameters. Our study addresses several questions about galaxies and O6. The one I will address in this talk is, how well do models of the CGM reproduce the dependence of O6 incidence on the mass of star-forming host galaxies? We find that at best, model predictions only agree with the measurements over limited mass ranges. They do not agree with the shape of the mass dependence. This is an empirical scaling that does describe the mass dependence pretty well. The quantity on the left is the average O6 column density within a virial radius of the host galaxy. This average is proportional to the star formation rate of the host galaxy divided by the product of the host halo virial temperature and the projected area out to a virial radius. We also show an equivalent form of the proportionality. To go from our heterogeneously selected data to these averages, we start with the star-forming galaxy subsample of our dataset and use curve fitting to produce a parametric description of the typical O6 column density as a function of host galaxy stellar mass and impact parameter. We then average this parametric description out to a virial radius, assuming the O6 distribution is spherically symmetric. We do this for 6 stellar mass bins, each of which is informed by at least 19 measurements. These curves are predictions for the average O6 column density as a function of host galaxy stellar mass. The predictions come from the Eagle simulation, the Chu and Bregman 2018 model, the illustrious TNG simulations, and we also show that scaling relation. The curves resemble broken power laws. We can summarize them with 3 numbers: a low mass slope, a break mass, and a high mass slope. The high mass slopes are all pretty similar. Massive halos can collisionally ionize oxygen more than 5 times. The big differences are in the break masses and, especially so, in the low mass slopes. The little bundle of line segments at the bottom right shows a rough by-eye estimate of the slopes, and they're all pretty different. The Chu and Bregman model is interesting because it agrees with the dwarf galaxy O6 measurements, unlike the simulations. Their model halos are spherical and in a steady state. There are no explicit dynamics in this model. The dwarf galaxy O6 arises through the photoionization of ambient low-density gas in these steady-state halos, implying that perhaps the dwarf galaxy CGM is actually pretty simple, at least in the phase seen in O6. The descriptiveness of the scaling relation also points to a potential unity or simplicity of the O6 generation mechanism, though this descriptiveness could also just be coincidental. This results in the details of the full analysis of O6 in gaseous halos spanning 3 decades in stellar mass will be published soon as Tchernyshyov et al., so keep an eye out for that. Thank you for your attention.